Good afternoon. Now, I have now the privilege to introduce you Professor Jeff Steinhauer. Now, let me tell you what I think this colloquium is quite interesting. This, I would say, in some sense, is more interesting than others. I'll make that case now. And the reason is because we have many seminars focused in one field of research, and this one is a good example when two different areas come together, being condensed matter physics and astrophysics. Now, Jeff is visiting us at Centra, the Center for Astrophysics and Gravitation. And of course, if you want to talk with him, I hope you do so. You can go to the fourth floor. You get out of the elevator. You go right and then
left and then right.
And then right. You check on the doors and you ask around and you can discuss with him. Okay, I don't remember exactly what is the number of the office. Now, as you see, he is working in Technion, Israel Institute of Technology. He's a full professor there, and he's quite active in this kind of research field, which I say with some colleagues is create, let's say, almost a new line of research, combining and using, let's say, as you say from the title, some acoustics, I would say, I will explain this better, how you can mimic some of the behaviors up to a point about black holes, and it's very at a science subject. With no further ado, let me just for final reference, Jeff is visiting us. He chose Centra to visit us. Thank you very much for coming. It's been
my pleasure.
I think in the future you will do other actions. Be attentive because I hope that things will be quite successful. And I hope you enjoy this presentation. With no further ado, Jeff, thank you very much for coming. Thank you.
Thanks. Thanks. Thank you, Elidio, for that very nice introduction. So, I would like to tell you about spontaneous Hawking radiation in a sonic black hole. So this is, I'll explain to you what Hawking radiation is, what a sonic black hole is. And this work builds upon a rich theoretical history, beginning with Jacob Bekenstein, who said that black holes should have entropy and temperature. Before Bekenstein, it was thought that a black hole was basically a featureless object. Then Stephen Hawking pointed out that a black hole should radiate at the very temperature predicted by Bekenstein. So that's Hawking radiation, this radiation that comes out of a black hole. And in making his prediction, he combined general relativity with quantum field theory. So that means it's semi-classical. General relativity is a classical subject. I don't know if, since I see there are many young students here, you maybe study general relativity. It seems very difficult, but it's classical. And he combined this with quantum field theory. So this is considered a first step towards reaching a theory of quantum gravity. And quantum gravity would be a replacement for general relativity that would include quantum effects. So Hawking's, the radiation that he predicted would be at a temperature, it'd be like black body radiation with a temperature given by the surface gravity of the black hole, and c is the speed of light. Now the problem of observing Hawking radiation from a real black hole is that the Hawking temperature should be extremely low. For a black hole of a few solar masses, for example, which would be a typical astrophysical black hole, the Hawking temperature should be less than a microkelvin. So it would be totally overpowered by other sources of radiation, such as the cosmic microwave background radiation, which are at much higher temperatures. But perhaps one could find very small black holes, and they would have a higher Hawking temperature because the wavelength of Hawking radiation is on the order of the diameter of the black hole. So a smaller black hole has a shorter wavelength, and that means a higher temperature. So perhaps primordial black holes could be found. These would be primordial black holes created in the early universe. And maybe they would be very small, and so they would have a higher Hawking temperature, but nobody has found those yet. Another possibility would be black holes at the LHC, the Large Hadron Collider in Geneva, and perhaps black holes would be created in the particle accelerator. And so now I'd like to mention very briefly searches for these black holes at the particle accelerator. First, we should think a moment about what Hawking radiation is. So here's the event horizon of a black hole. And so this is the Hawking radiation coming out of the black hole. And this is a Hawking particle, we can say. And it has a frequency and an energy greater than 0. Like all the particles around us in our world, all the particles have positive energy. However, inside the black hole, a particle which is trying to escape the black hole but being pulled in by the gravity has a negative energy. So we have nothing like that in our environment. And so you could have a pair of particles with 0 total energy. And this is Hawking radiation. So this is Hawking radiation is the production of these pairs with 0 energy. And so they can occur spontaneously from nothing. In the nothingness at the event horizon, these pairs can appear because they don't require any energy. And Hawking predicted a thermal distribution of pairs. So it's not just one frequency, it's all the frequencies and all the standard model particles. Standard model particles. All the different types of particles would be produced. Now this is what is called a semi-classical black hole. This is Hawking's calculation is semi-classical, as I mentioned. It has a general relativity, which is classical, and the quantum field theory, which is quantum. And this is his result. So in the searches for black holes, they search for semi-classical black holes, like we just mentioned. And that means they're looking for thermal emission of all the standard model particles. They're looking in their detector to see some extra radiation of all the different kinds of particles. So that's one type of search. Another kind of search is searching for quantum black holes. And when they say quantum black holes, they mean a black hole which is so small that it only really breaks up into 2 particles. So just decays into 2 jet final states, as they say. So for these very small black holes, you can't think of it as being somehow in thermal equilibrium or something. It's too small. So the semi-classical black hole searches, there have been many, also quantum black hole searches, but they haven't found anything yet. So now I'd like to mention a few topics related to black holes, interesting subjects related to black holes that will be relevant for this talk. First of all, the information paradox. The information paradox was presented by Stephen Hawking himself, and the question is, what happens to information that falls into a black hole? So if you throw a computer into a black hole or something, where did the information in the computer go? Because the Hawking radiation that comes out of the black hole is totally random, according to Hawking's calculation. So, so you threw information in, but what came out had no information. So where did the information go? So as Hawking said, the information which crosses the event horizon is irretrievable. The phase of the Hawking radiation that comes out can't be predicted. It's totally random. Thus, there is uncertainty beyond the Heisenberg uncertainty principle, which violates quantum mechanics. So that's the information paradox. And you can see the information paradox most clearly if we think about an evaporating black hole. Due to the Hawking radiation, the black hole will lose mass and will shrink away until the black hole is completely gone. And all that's left is the Hawking radiation. So there really the question of if information fell into the black hole, or if the matter which was used to form the black hole had information, then where did that information go? And the answer to the question may lie in quantum gravity. There are many, many articles that one can find in the literature giving possible solutions to the information paradox. And probably most of them are based on quantum gravity. The idea is if we repaired general relativity, came up with a quantum version, that would somehow explain the information paradox. Another issue is Planck scale physics. So here's Hawking radiation coming away from a black hole, and it reaches us, it reaches infinite distances with some finite temperature, and that means some finite wavelength, not infinite wavelength. So if we trace this back to the black hole, it gets blue shifted. The wavelength gets shorter and shorter as we approach the black hole until it really approaches zero at the event horizon of the black hole and goes below the Planck length scale. And no one knows what the laws of physics are for length scales shorter than the Planck scale. So it seems that Hawking's prediction, his calculation, is somehow based on length scales that no one knows what the physics is at those length scales. So that really calls his entire calculation into question. When the calculation was first made, people weren't sure if it was correct. So this inspired Bill Unruh at the time in 1981 to come up with the idea of a sonic black hole, an analog black hole in the laboratory where sound plays the role of light. And he wrote in his paper, black hole evaporation is one of the most surprising discoveries of the past 10 years. So he was trying to check Hawking's calculation using this sonic black hole. And he came up with the same Hawking temperature, only now G is the analog of the surface gravity, and I'll explain what that is later. And CS is the speed of sound. So there have been many systems proposed as possible sonic black holes. For example, Bose-Einstein condensates, which is what I'll be discussing today. And there are many, many articles discussing this possibility, theoretical articles. Other theoretical possibilities are superfluid helium-3, electromagnetic waveguides, ultra-cold fermions, rings of trapped ions, superconducting circuits, light in a nonlinear liquid, exciton-polariton condensates, magnons in a magnetic wire, and Weil semimetals. On the experimental side, my group has been studying sonic black holes for more than a decade, and we've made a systematic study where we first learned to create sonic black holes, and then we learned to observe small quantities of phonons. In our experiment, the Hawking radiation is phonons. And then we were actually able to observe the Hawking radiation. And that's what in some of these last articles, and that's what I'll be discussing today. Another area of active study is surface waves in water. In water, you can actually see a classical version of Hawking radiation, it's called stimulated Hawking radiation, where you send a wave in that hits the horizon and that generates pairs of waves. And so it's not the spontaneous quantum effect, but it's a classical version. And then nonlinear optical fibers is actually another area of study where they've actually also seen this classical stimulated effect. And exciton-polariton condensates are also, they're working on seeing Hawking radiation in this system. So here's a picture of our sonic black hole. So this sort of whitish region and the gray region, that's the sonic black hole. It's a long, thin thing. It's not a sphere like a real black hole. It's like a one-dimensional, thin black hole. And what you're seeing here is about 8,000 atoms. This is a Bose-Einstein condensate. So this is very small. This is only 8,000 atoms. What you're seeing here is about 0.1 millimeters long. And it's very, very cold. It's even colder than the typical Bose-Einstein condensate. It's less than 1 nanokelvin, the temperature of this gas. These atoms are forming a form of gas. So this thing is flowing from left to right. And here it's flowing slowly, and over here it's flowing faster. So if we can, in its fact, it's flowing faster than the speed of sound. So in this region, if we consider a sound wave going against the flow, it feels like it's going forward, this sound wave, but it's not. In the laboratory frame, it's being swept to the right by the fast flow. So the sound wave is unable to reach this point. It's like a particle trapped inside of a black hole. It can't get out. So this point is the analog of the event horizon of the black hole. And this region is inside the sonic black hole. A sound wave on this side can go forward because the flow is slower than the speed of sound. So this is like outside the black hole. So we're going to look for pairs of sound waves, one on this side and one on this side. Now the sound wave on this side is Doppler shifted. They're both Doppler shifted, but this one is very much Doppler shifted because the medium is moving to the right relative to the observer. We could say the observer is moving to the left faster than the speed of sound. And it's Doppler shifted so much that the frequency is negative. So if the frequency is negative, that means that the energy of the particle, of the particle of sound, is negative. So like, for example, you've probably seen in quantum mechanics that this would be the energy of a photon, h bar omega. It's also the energy of a phonon, a particle of sound, where we plug in the frequency. And since the frequency is negative because of the Doppler shift, the energy of the phonon is also negative. So we can have a pair of waves, a negative energy one and a positive energy one. The sound wave over here has positive energy, the phonon, so with zero total energy, and that's the Hawking radiation. And that's what we're going to look for. But first I'll tell you a bit more about the experimental system. So the reason that this thing is long and thin is that it's trapped in a laser beam. These atoms are trapped at the focus of a laser beam. So here's a focused laser called the trapping laser. And at the focus there, the atoms are held there. And it's inside a vacuum chamber. This rectangle is the vacuum chamber. And there's a laser coming from above to image the atoms. So we saw this picture. The way that this picture is acquired is a laser beam goes through the atoms, through the cloud, and these atoms have an index of refraction. This gas has some index of refraction, and that's how we see it. It's like a lens. You know, how does a lens focus light? Is because of the index of refraction. So the light gets a phase shift as it goes through the cloud due to the index of refraction, and that's what gets imaged onto the camera. We have a reference beam, and we see the phase shift of the light. And there's also, there's a high resolution lens down here below, and the laser goes into the lens. And then there's also an anti-gravity coil because the laser beam is too weak to support the atoms against gravity. So there's a magnetic field gradient which counteracts gravity. So this from above, this is what the apparatus looks like here. What we were looking at is over here. The atoms are here. The cloud is over here. The beam enters over here for trapping the atoms. And we could see that the beam is going through these paper tubes. And the reason that all the laser beams are going through paper tubes is because, as I mentioned, the cloud is extremely cold. And so if the laser beam moves a little bit due to the air in the room, just the motion of the air in the room moves the beam and heats up the cloud of atoms. So the air tubes prevent the beams from feeling the breezes in the room. Now, I mentioned that it's flowing slowly here and fast here. That's because the atoms are flowing over like it's like a waterfall. It's a step potential. And so when they flow over the edge, they get accelerated. The potential energy is converted into kinetic energy, and they start moving faster than the speed of sound. So this step is created by another laser beam. So this is a blue laser beam. And a blue laser beam, blue means blue relative to the atomic resonance. More higher energy than the atomic resonance energy. So if it's blue relative to the resonance, then it repels the atoms. One can prove that. So this is repulsive for the atoms. So when the atoms are in the beam, if they come out of the beam, they lose all of that repulsive energy, and it's as if they've gone over a potential step, and they get accelerated. So, so then this beam is like it's like a elliptical shaped laser, Gaussian laser beam, which is moving coming towards us, but it's been cut in half by a knife edge somewhere in the imaging system, and then imaged onto the atoms. So there's this very sharp edge here, and then of light, going from light to dark, and then the beam is moved slowly to the left. Now, if we go into the reference frame where the beam is not moving, it's as if the cloud of atoms is going to the right. So the cloud of atoms is going to the right and pouring over the potential step and being accelerated to supersonic speeds. So here's just a picture of some of these lenses that take this blue laser beam and image it. These lenses image it onto the atoms, and then it comes in from over here. So here the laser beam comes in over here, and there's a mirror somewhere else in the imaging system, and the mirror rotates, and that moves the beam along the atoms, which is as if the atoms are moving. So we also sometimes take pictures without any waterfall potential, without any, it's just a stationary Bose-Einstein condensate. It looks like that, and we use that to adjust the magnetic fields to make sure this stays in the middle. Because we're going to take many thousands of images. We repeat the experiment thousands of times during many days in order to be able to see the Hawking radiation, because the signal is very small. Okay, so here's what the apparatus looks like from farther away. What we saw was over here. A lot of this optics here, there are lenses and mirrors and things, and that's for the first stage of cooling the atoms. The atoms are cooled by laser cooling. That's the first stage of the cooling, is lasers. Any direction the atoms try to move, a laser stops their motion from every direction, and so that the atoms slow down, so that means they're getting colder. So that's laser cooling. And here's here's another view with all these mirrors for laser cooling. And here's the lower level. What we saw was up there before. It was up there. This is a lower level with a lot of this optics for imaging, and also with these air tubes. And here's another table which has just some lasers on it. The blue boxes are lasers, and they go over to the other table through optical fibers. Okay, so now getting to the Hawking radiation, we want to see the very weak sound waves, phonons, traveling into the black hole and out of the black hole. And we're going to look for that. But first, what temperature do we expect? So what temperature of radiation are we expecting to see? So the predicted temperature is given by this formula, where the Hawking temperature is related to the surface gravity and the speed of sound. So the surface gravity is given by the derivatives of the flow velocity and the speed of sound evaluated at the horizon. So what that means is, if let's integrate this picture vertically, we get a density profile which looks like something like this. You could zoom in on that. So density profile looks like this. And so here is the slow region, and then over here is the region that's flowing fast to the right. Here's the horizon, the transition from the slow motion moving region to the fast moving. There's more density in the slow region because if you think of like a conserved current, where the velocity is slow, the density should be high, and when it starts to move fast, the density gets smaller. It's like cars driving on the road or something. They're closer together when traffic is going slowly. So anyway, so the density here is high. Okay, so here's the horizon, and we want to evaluate the derivative of the flow velocity here and the speed of sound, given by this formula, to get the surface gravity. So the speed of sound, we were looking at the density here, we could translate density into speed of sound because we know the properties of our Bose-Einstein condensate. So the speed of sound we could get. But now for the flow velocity, what we do is we assume a constant current, as I mentioned. So the density times the velocity is a constant. So we can convert the derivative of the velocity to a derivative of the density. So here we have a derivative of the density. So we can extract both the speed of sound and the density derivatives from this picture, and we could get the Hawking temperature. So now I'll show you as a function of time the predicted Hawking temperature. That's these blue circles. So as a function of time after the horizon is formed, we expect sort of this constant. This is the log of the Hawking temperature, this constant Hawking temperature of 0.4 nanokelvin until the very latest times when it goes down. And this is very different from a real black hole. In a real black hole, as the black hole shrinks away, the Hawking temperature goes up and up. But here, the Hawking temperature just sort of stays constant and goes down a little. OK, so that's the prediction for the Hawking temperature. Now let's actually observe the sound waves and see what temperature they actually have. So in order to observe these very small density waves with a thermal distribution of them, it's not even at one frequency that we could look for, one wavelength. It's a distribution of wavelengths. So in order to see this, we follow the suggestion in the literature, and we use the correlation function. So we're expecting that this point is emitting pairs of waves, one coming out and one coming in. So here's the density profile, just integrating this image vertically. We expect this horizon to be emitting waves going this way and this way. So if we consider 2 points which are equal times from the horizon, x and x prime, then equal propagation times from the horizon, then we expect density correlations there. We expect the density wave here to be correlated with the density wave there, since they're emitted together as a pair. So if we look at the correlation function, here's the correlation function. It tells you if x and x prime, here's the density fluctuation at x, and here's the density fluctuation at x prime. You multiply them together and take an average over thousands of repetitions of the experiment. And if this comes out different from 0, that means they're correlated. That means that this number is always positive every time this number is positive, or this number is positive every time this number is negative. So the correlation could be positive or negative, but if it's not 0, that means it's not random. These waves are created in pairs. So we use this so if you plot this correlation function as a function of x and x prime, you expect a band of correlations where each point on the band is a pair, x and x prime, which are equal times from the horizon. So we're going to look for this band. We're going to repeat the experiment thousands of times, compute the correlation function, and look for this band. And now we expect the band to be actually negative correlations. Along this band, these numbers have opposite signs. And we could understand from this article that negative correlations means positive mutual information between the inside and outside of the black hole. So sort of the information is contained in the correlations between the inside and the outside. So let's see the experimental results. So each of these correlation functions, these are correlation functions at 15 different times. And we can see in most of these correlation functions a band. I hope that you can see it, starting from the middle and going up to the left. And these bands are the correlations between the Hawking and partner particles. This is our observation of Hawking radiation. And all of these correlation functions together required a total of 97,000 repetitions of the experiment, which corresponds to 124 days of continuous measurement. So now this region is labeled spontaneous Hawking radiation, these 6 pictures. So let's zoom in here on the spontaneous Hawking radiation. So we'd like to convert this into a temperature. We had the predicted temperature of 0.4 nanokelvin, is this radiation, this band that we're seeing, is that somehow 0.4 nanokelvin radiation, or is it some other temperature? So we'd like to convert this to a temperature, but this is a position space picture. So this is x and this is x prime. How do we convert that to a temperature? Well, we developed a Fourier transform technique. We could just take the Fourier transform of this and ask which wavelengths are involved. But instead of doing that, I'm going to give you a more intuitive picture to get the temperature. If the band is deep, that means more Hawking radiation. The more radiation there is, the deeper the correlation band. And that means higher temperature. Higher temperature radiation, there's more of it. The sun emits more radiation than, say, I don't know, a room temperature object. So if we just looking at the depth of the band, we get these green points. This is due to a measure of the quantity of Hawking radiation. And we can see during the spontaneous period, the green points agree with the blue points. So they're at the correct temperature for spontaneous Hawking radiation. Now, another way to get a temperature out of this band is by the width of the band. The narrower the band, the shorter the wavelength. And shorter wavelength means higher temperature, higher energy, higher temperature. So from the width of the band, we get the red pluses, which also agree fairly well with the blue circles during the spontaneous period. So during this spontaneous period, we really see quantitative agreement with Hawking's calculation. We see that the Hawking radiation seems to be spontaneous because the quantity is of the correct quantity that one would expect for Hawking radiation. We see that it's thermal in the sense that the height of the spectrum, the green points, this quantity, the height of the spectrum agrees with the width of the spectrum. So it's a thermal-like spectrum. So we see that it's thermal. We see that it's stationary, like a black body. A black body radiates at with a constant radiation rate. And we see it's stationary because this is pretty much a constant during the spontaneous period. And it's at the predicted Hawking temperature. It all agrees with the blue circles. So this really confirms Hawking's calculation. We've created a system which should, like a black hole, should also obey Hawking's calculation, meets the requirements of his calculation, and we indeed see the Hawking radiation. So this confirms his calculation. But if we look at earlier times, we see something strange. We see that there is a predicted Hawking temperature, but there's almost no actual Hawking radiation. So this seems strange. We have a black hole with some surface gravity, but little or no Hawking radiation. So I have a couple explanations for this. The first one is probably, it's not really correct, but it's entertaining. So I'll tell you the first possibility is this dashed curve seems to be some theoretical curve which agrees with the experiment. And this dashed curve corresponds to the gravitational collapse of a cloud of dust. So now we're talking about a real black hole, which is created from a cloud of dust. Black holes are thought to often form by some collapsing, some matter which is collapsing due to gravity. So one model would be a cloud of dust. And if you had a cloud of dust with 170 solar masses, it would collapse and form a black hole with the same Hawking temperature as our black hole. And the radiation, we could then, it's been computed in this article, what the radiation, the flux of radiation emitted during this process of collapse would be as a function of time. And one can convert that into a temperature because the radiation should go like the temperature to the fourth. That's the Stefan-Boltzmann law. And so one gets this curve, this black curve, this dashed black curve, which agrees nicely with the measurement. But I have no reason to think that our black hole should have anything to do with a collapsing cloud of dust, our sonic black hole. Another explanation can be seen is gray solitons. Now, if we if we here, these are the pictures. This is the ramp-up period where there was no Hawking little or no Hawking radiation, and here's the spontaneous period where you could see this band. In this period, you can also see this strange pattern in this area of the correlation function with the black and the white. And this strange pattern moves away. It starts to move away, and here it's moving down towards this corner even more and more until it's gone. And we see the Hawking radiation. Now this strange pattern, I believe, is gray solitons. A gray soliton is a kind of excitation that can be in a Bose-Einstein condensate. It's like a little density minimum which slowly moves away. It's sort of like a sound pulse, but it goes a bit slower than sound. And it will move in this direction. And when the black hole is created, there's this sound pulse, that gray soliton, that moves this way. And so while these gray solitons are still near the horizon, they apparently make it so we can't see the Hawking radiation, or they destroy the Hawking radiation. So I think that this is what's destroying the Hawking radiation. So maybe, in a sense, it's sort of similar to the ring down of a real black hole, ring down. They say that recently it's been observed in the past decade that two black holes can collide and form a single black hole, and then it rings, and then it oscillates and rings down, and it sheds away and then reaches the stationary configuration after it rings down. So it's shedding away its extra energy of the collision when it's ringing down. And so maybe this is sort of similar. When the black hole is first created, it sheds away the extra energy in these gray solitons. So that is probably, I think the gray solitons probably explains why there's little or no Hawking radiation in this region. Now, what happens, okay, then one more thing I'd like to mention about this spontaneous period is the lack of dispersion. This is, I guess, sort of technical. For people who are interested in Bose-Einstein condensates, here's a theoretical calculation of what our pattern should look like using a certain model. And they see these extra fringes. And we don't see that. We only see one fringe. And these fringes are due to the fact that our dispersion relation is not truly linear. Light has a linear dispersion relation. The frequency is proportional to the wave number. Omega equals ck. In our Bose-Einstein condensate, that's not precisely true. It has a little bit of curvature. Omega is a function of k. And so that creates these extra fringes, and we don't see them. I think it's because our system can't produce high k's. Our horizon is not sharp enough to produce the high k's required to see this pattern. Anyway, okay, now let's get on to the next step, which is stimulated Hawking radiation. At some late time, at the end of the spontaneous period, an inner horizon forms. Our black hole has an inner horizon. Real black holes also have inner horizons. You've probably all heard of the event horizon of a black hole, but black holes also have an inner horizon, two horizons. Most black holes, because if a black hole has electric charge, or if it's rotating, then it has an inner horizon. And most black holes, maybe all black holes, are rotating. Real black holes are rotating. So they have inner horizons. So now, when the inner horizon forms, suddenly you could see the quantity of Hawking radiation goes way up, and the spectral width goes down, and it no longer agrees with the surface gravity. And so now let's understand that a little bit. First, I'll explain what the inner horizon is. So here's the potential as a function of time which creates the sonic black hole. So zooming in, here's what the potential looks like. The Bose-Einstein condensate sits here in this minimum, and then the minimum moves to the right, and the Bose-Einstein condensate flows over this step. So this is both a combination of the trapping laser and the blue laser that made the step. So anyway, the Bose-Einstein condensate flows over the edge and is accelerated to supersonic speeds. But then it goes uphill. After it's accelerated to supersonic speeds, and we have the sonic black hole, it goes uphill. So that means at later times it slows down again, slower than the speed of sound. So at some point over here, the black hole sort of stops being a black hole. You're no longer in the supersonic region. So, and that's the inner horizon. It's like in a real black hole. If someone fell into a real black hole, they would be in the black hole, and then they would go through the inner horizon, and it would be like they came out of the black hole again. But they wouldn't be able to get home. They would be stuck in the middle of the black hole, but at least they wouldn't have that strong pull of gravity like as when they were really in the black hole. So that's the inner horizon. So what happens with this inner horizon? What does it do to the dispersion relation? So, okay. Here is the dispersion relation of the Bose-Einstein condensate. This is outside. This is where it's just you could very slowly moving Bose-Einstein condensate. And here it is omega as a function of k. And it's almost linear, but then it curves up at the end. That's why it's different from light, because at short wavelengths, at large k, it curves upward. Now one can ask, does that happen for real light? Like if we went to very, very short wavelengths, is the dispersion relation of light still linear? Meaning, is the speed of light the same for light at, say, light frequency as for extremely short wavelength light? And no one knows the answer to that question. Once we're considering wavelengths shorter than the Planck length, which is around 10 to the minus 35 meters, so very, very short wavelengths, no one knows what the speed of light is there. It might be different. Light might do that. No one knows. It's been said that it should occur well beyond the Planck scale, this Lorentz violation. Anyway, in our Bose-Einstein condensate, there's no doubt, we definitely know that the dispersion relation curves upward like this. So now let's look inside the black hole. We have to put a Doppler shift. So that means the speed of sound, the slope of this is the speed of sound, is going to be different. In fact, it's going to be negative slope because there's so much Doppler shift that we said that the frequency becomes negative. So the slope is negative. But remember that it curves up. So it goes parabolic. So at some point, it curves back up, the dispersion relation. So that means that there's this particle here, which has zero frequency. So let's consider this particle, this wave right here. It has omega equals zero frequency, and the slope of the dispersion relation is a negative slope. That means it goes from right to left. So in other words, there's a wave in here which can move the wrong way in the black hole. It could go from inside the black hole out towards the horizon, and it has zero frequency. So this zero frequency wave can be created for free. It's an instability. The system is unstable, and the inner horizon, which is over here somewhere, creates these zero frequency waves. They move out and hit the horizon and stimulate pairs. So that's why when the inner horizon is created, we suddenly see much more Hawking radiation, because there are these special waves which are created there, move out, and stimulate Hawking radiation. And this is called, this effect was predicted by the Ted Jacobson's group, and this is called Bogolubov-Cherenkov-Landau stimulation. And if this were to, this probably doesn't occur in a real black hole, but no one could really be sure because no one knows what the dispersion relation does at very short wavelengths. So that's why here at later times, so this was the spontaneous Hawking radiation. Here at the later times, we see it becomes very strong. The band is much easier to see than in the spontaneous period because there's a lot more Hawking radiation. And at even later times, it gets even stronger, where you could see here the scale goes to 2, whereas here it's going to 0.1. So now it's very, very strong, and it starts to look monochromatic, because here the waves that are coming from here and going to here are at a very definite frequency, so they're stimulating single frequency waves. And that's why you see this monochromatic behavior. So that's why the amount of Hawking radiation goes way, way up once the inner horizon forms. And the spectral width is going down. It's becoming monochromatic. Now that sounds a little bit like a laser. A laser, due to some process, the wavelength, all the radiation emitted by some gas becomes single frequency, becomes monochromatic. And there's something called black hole lasing, which is just that. But what we see is not black hole lasing. Black hole lasing is very similar to what we see, but not exactly. In black hole lasing, the horizon emits particles, and they come and hit the inner horizon, they bounce off and hit the outer horizon again, stimulating more particles. And they go back in, bounce off, and they go bouncing back and forth. And this is called black hole lasing, invented also by the Ted Jacobson group. And that's different from what we saw, because what we saw, the particles were created at the inner horizon and went out. They weren't created here and bounced back and forth. So it's almost the same thing, but not exactly. And black hole lasing should be random, stochastic, and should occur very slowly. What we see is deterministic and fast, and that's how we use numerical simulations to see that what we see should not be the black hole lasing. So, in conclusion, we see spontaneous Hawking radiation, and we see that it is stationary and thermal and at the expected temperature. We make 6 independent measurements of the Hawking radiation during the spontaneous period, as Hawking predicted that it should be spontaneous. And so during that period, we make 6 independent measurements of it. So this really quantitatively confirms Hawking's calculation. We also see stimulated Hawking radiation, and it's of the Bogolubov-Cherenkov-Landau type, rather than black hole lasing. Now, what did we learn about real gravity? What are the implications for real gravity? My interest in studying sonic black holes is not just for the fun of it, it's to actually learn something about real black holes. So what did we learn? We learned it confirms Hawking's calculation quantitatively, including the thermality of the spectrum, the temperature, the spontaneous emission, and the stationarity. Now the stationarity verifies the correspondence with black body radiation. So a black body, like a star, radiates at some constant rate, and we see that Hawking radiation also does. The thermality is the basis for the information paradox. So the fact that Hawking radiation is thermal means that it's random, and that means that there's an information paradox that someone really would need to solve for a real black hole. Our sonic black hole doesn't have an information paradox, but a real black hole does, and one should find a solution. It's necessary based on what we see. The temperature links Hawking radiation with black hole entropy. That means, as we mentioned at the beginning, Jacob Bekenstein came up with a certain temperature for the black hole entropy, and that's the very same temperature that we see for the Hawking radiation. So we verify that there is this correspondence. We verify it on the Hawking radiation side. Also, we see that the Hawking correlations between the Hawking and partner modes are of the predicted magnitude. And we saw that band. Here's the correlation band. I should have mentioned, this is an average of the six observations during the stationary period. So here you could really see the band very clearly. So these correlations are of the predicted magnitude, despite the underlying quantum structure. So it's thought that a real black hole should have quantum gravity, meaning, well, the universe should have quantum gravity, and that might alter the Hawking radiation. There's an idea that maybe there should be a firewall, for example. There's a theory that at the event horizon of a black hole, maybe there's a firewall, and the firewall breaks the correlations between the Hawking radiation and the partner particles. And that's why there's a firewall. You say, why is there a firewall? Because it breaks the correlations. And what breaks the correlations? The firewall. But anyway, so there might be a firewall. And we also have a quantum structure in our black hole, because our Bose-Einstein condensate is made of point-like particles. And so that's our quantum gravity for our black hole. But we have no firewall in our system, because we see the correlations are just as one would predict. So thank you.